Hey, hi, welcome to the video number 5 of wind turbine blade design. Now, in this video, what we will discuss is how to pitch the blade of the wind turbine and what are the advantages, why do we do it. So, as you can see on the right hand side of your screen, this blade has, can you see this root? We have to twist it. That means we have to change the angle of the blade itself. We have to change the angle of the complete blade. Why do we do it? Remember, in the last video what we did was we changed the angle of the elements, but in this video we are changing the all the angles. That means we are changing the angle of the blade itself. Now the reason is, remember in the last video when we were designing the twist angle, this was the angle. This angle right here was our twist angle. This angle was our twist angle. But now, as you can see, we have put in one more term. That is the pitch angle. The reason is, now imagine in the last video we were discussing about element which has a tip speed ratio of 8 right over here. This element has the tip speed ratio of 8. But what will happen if the velocity of wind changes? So it's very clear that if the velocity of wind changes, the tip speed ratio has to change. But our twist design is for a particular tip speed ratio. So our design of our twist was for the tip speed ratio of 8, isn't it? This was the tip speed ratio for which we designed the twist. But now what has happened is the tip speed ratio has changed suddenly because the velocity of wind is random. So the tip speed ratio has changed. So we should have some tool in our hand such that we can control the angle to maintain this best possible angle of attack. Please. The concept will get more clearer when we draw the velocity triangle, but for now just imagine this is an element. We are speaking about a single element. I don't want you to get confused. This is the velocity triangle of the element which is located here, the final element at 5 meters. So we are speaking about a single element right now. Now in the last video what we did is we designed the twist angle for this element at a tip speed ratio of 8. That means if the tip speed ratio is 8, we do not need to pitch it because we have already designed the twist such that the alpha will be the best at 7 degrees. So we have designed the twist for tip speed ratio of 8. Exactly at 8 tip speed ratio, our wind turbine, at least this element, this element will be very happy. It would generate the best possible coefficient of power because it has the best possible lift to drag ratio because alpha is 7 degrees. But what will happen if the tip speed ratio will change? If the tip speed ratio changes, then this guy right over here, which is angle of inclination, will change, and this guy right here will change because this is also phi, isn't it? So we have to introduce something which will compensate for the change in phi, because we have designed this twist angle beta for a particular tip speed ratio. But if the tip speed ratio changes, we should have some tool in our hand by which we can adjust, we can compensate for the change in for the change in tip speed ratio for which the blade is being designed. So I reckon it should be quite clear to you now that as the tip speed ratio changes, this angle of inclination phi changes, and we want alpha to be 7 degrees, and beta is designed for a tip speed ratio of 8. But tip speed ratio has changed, say for example to 9 or 10. So accordingly, we have to change the pitch angle theta p in order to compensate for the change in angle which is caused due to change in tip speed ratio, that means change in angle of inclination. So it will become more clearer when we draw the triangle. Now imagine this wind turbine is running at a tip speed ratio of 8, exactly at the tip speed ratio at which we have designed the twist. So if someone asks us what should be the pitch angle, what would you answer? We know we have already designed the twist for the tip speed ratio of 8. That means this angle beta is the difference between difference between phi and alpha. So we do not need any pitch. Why do we need any pitch? Because we have already designed it for that tip speed ratio, isn't it? So the pitch angle is 0 degrees when the tip speed ratio is 8, because that is the tip speed ratio for which we have designed the twist angle. So it has to be perfect. But now imagine if the tip speed ratio changes, what's going to happen? How will we pitch it? We have to pitch it. So for example, imagine the tip speed ratio is 10. Now what's going to happen is something like this. The best way to understand is, just imagine we have designed this blade element for a tip speed ratio of 8. When the tip speed ratio is 8, we know that angle of inclination should be 8 degrees. So let's write it down. So when the tip speed ratio is 8, angle of inclination, that means this angle right here, this is the angle of inclination, is equal to 8 degrees. Right? Now alpha, which is the angle of attack right over here, this is alpha, which is angle of attack. We want it to be 7 degrees. Why? Because we want the best possible lift to drag ratio. So this has to be 7 degrees. So that means this angle, which is our twist angle, I'm speaking about the tip speed ratio of 8. That means we have designed the wind turbine for the tip speed ratio of wind turbine twist for the tip speed ratio of 8. So in the previous video we have seen that this is the twist angle, which has to be 1 degree, because phi, as you can see from the triangle, is equal to alpha, which is angle of attack, plus the twist angle. So 8 is equal to 7 plus 1. So our twist angle should be 1 degrees. So our wind turbine is happy now. It is exactly at an angle of attack of 7 degrees. That means we do not need pitch, because it's already twisted at 1 degree. So this is our design TSR, so we do not need pitching. But see what happens when, now this is TSR, this is for the design TSR, which was equal to 8. But see what's going to happen when the TSR will change. These all are degrees, degree. So let's analyze what's happening, what will happen when TSR will change. Say for example the TSR now is 4 degrees. So let's copy this and paste it here. So now let's see what happens when the TSR changes to 4. So imagine TSR has changed to 4. So this angle phi has to increase, isn't it? Because the magnitude of this vector r omega, linear velocity, has decreased compared to the magnitude of the velocity vector of the wind. So naturally the phi has to increase. Now as the phi increases, remember we want our alpha to be 7 degrees. Now when the tip speed ratio was 8, our phi, which was our angle of inclination, this angle right here, was 8 degrees, right here, 8 degrees. But now this guy has changed to 14 degrees. So let's remove this 8 degree and write it 14 degree. So now this angle is 14 degree. 1 for 14 degrees, and the angle of attack is the angle of attack which we want. So we want it to be 7 degrees, so we can't change it, isn't it? Now beta is the twist angle. Now remember we have designed this at 1 degree. Now since we have designed it, we can't change it because it is a material. Now it is a constant. We cannot change the twist angle. This guy is a constant. So now I reckon it would be quite clear to you, the only thing that we can change is this angle, which is our pitch angle. Now I think it would be quite clear to you. So now we know that this angle of inclination is 14 degrees. We want alpha to be 7 degrees, and our twist angle is designed for the tip speed ratio of 8, so it is 1 degree. But if it is 1 degree, the angle of attack will become poor. So to compensate, we twist the blade. Now how much will be the twist? Now just see the velocity triangle carefully. You will observe this phi 14 degree has to be equal to, observe the velocity triangle very carefully, has to be equal to alpha, which is our angle of attack, plus beta, which is our twist angle, plus some mechanism which we will put in to change the angle of the blade, which we call as theta p, which is our pitch angle. Now 14 degree is our angle of inclination, and alpha is 7 degree and beta is 1 degree. So now the only thing we can change to balance this equation is this, which is our pitch angle. We have to change our pitch angle in order to balance the equation. So once the equation is balanced, our alpha is managed at 7 degrees. So that is our intention. That is what we always want, alpha to be 7 degrees. So now see the velocity triangle carefully. Phi is 14 degrees. We want alpha to be 7 degrees. Beta, which is our twist angle, is constant 1 degree. So naturally our pitch angle has to be 14 minus 7 minus 1, so it's 14 minus 8, which is equals to sorry, 6 degrees. I hope you understand the logic behind it. It's quite simple. It's quite simple. As the phi changes, as the angle of inclination phi changes, we want alpha to be constant. Beta, which is the twist angle, is designed for a particular tip speed ratio, say for example 8. But as the tip speed ratio changes, this angle of inclination changes. So to compensate, we want something which which can compensate for the change in the angle phi, because beta is the twist angle which we have already designed. It can't be changed. So we put a mechanism to change the complete angle of the blade, which we call it as pitch angle. So this is the concept of the pitch angle. Now the question is, what about the other elements? This was a single element, so now we know that if we pitch the blade at 6 degrees, this element would experience the best possible left to drag ratio. But what about the other elements? There are so many elements along the length of the blade. What about them? Will be they experiencing the same left coefficient and drag coefficient? No, they won't be. For that, just make a spreadsheet and plot all the elements. You would observe that as you change the pitch angle of the blade, you would get a graph something like this. This is your tip speed ratio, and this is your CP. We'll get to this later. We'll get to this concept later because we haven't got into the forces up till now. Once we get into forces, we will exactly know the amount of force which is acting on the blade element and the power which is generated by them. So it will become very interesting. The curve would be something like this. So as we change the pitch angle, we can improve the coefficient of power, but we'll get into it later. But for now, I just want you to understand that we design twist for a particular tip speed ratio. But if the tip speed ratio changes, we have to compensate that change in angle of phi. For that, we pitch the blade. So when the tip speed ratio was 8 right here, our pitch angle was 0 degree. We didn't want to pitch it because that was the tip speed ratio for which we have designed it. So naturally we didn't design any pitch. But as the tip speed ratio changed, then we need to pitch the blade. So here we can see as the tip speed ratio changed to 4, we have to pitch the blade by 6 degrees in order to achieve alpha at 7 degrees. So this is the concept behind pitching. In the next video, we will see how we can pitch the complete blade, and we will analyze all the blade elements together. And we will get into now. Most of the angles are finished. We have finished with pitching angle, twist angle. Now we will get into forces, and the now we will get into the design of complete blade. Up till now we were into elements. So for this video, I hope you understand that pitching is very important to achieve the best possible CP. It depends. We have to change the pitch according to the change in tip speed.